group element raised to the group order is the identity. Okay, well, if I raise this to the p to the 8th power and get the identity, where does that put this thing?
In the order?
That puts it in H. That's what it means to be in H, is the p to the 8th power is the identity. Okay, you can probably guess what's going to happen with the other piece. What was that?
You substituted the x1 back into it.
Right. Okay, similarly, if I take this other thing, x to the p to the 8 y, and raise it to the m, then I get x to the p to the a m, all to the y, and that again is the identity. So that means x to the p to the a y, that belongs to k. All right, so that means x, which was equal to x to the mz, x to the p to the a y, that belongs to hk, because this is something from h, this is something from k. And x was just any old group element. So that means hk encompasses the entire group. So that means the product of H and K really is the entire group G. All right, but wait, there's more. So because H and K are both normal subgroups of G, HK intersect trivially, and H times K is the whole group. What does that mean?
H cross K.
That's right. This means G is really an internal direct product of H cross K, which means it's isomorphic to the actual external direct product of H and K. Whew. Okay, that was worked out. That was the easier of the two steps. The other step is a little bit harder, and I might need help from the book again. Okay, there's one more thing though that Gallian proves about this whole situation. In addition to proving that G is the internal direct product of H and K, and this is actually quite useful. He tells you what you should expect the orders of these groups to be, which is nice. Okay, I'll show you why it's nice in just a minute. Okay, so we also claim that the order of H is e to the a, and the order of K is equal to m. All right, so here's why. Yeah, we're going to use some more number theory here. Okay, here's why. Okay, first of all, first I claim that P doesn't divide the order of K. All right, and the reason for that, now I'm partly stalling here because I'm trying to remember what the exact reason was. Okay, why doesn't P divide the order of K?
Because P doesn't divide M?
Wait, what?
Because it doesn't divide M? Or?
Oh, but we don't know yet that the order of K is, that's the only thing.
Oh, okay.
We will soon know, but we don't know quite yet. Okay. I think, so I was trying to think of what would be the most elegant reason why. I think I'm just gonna go with the reason I have at hand. Okay. If it did, if P did divide the order of K, y'all remember in class when we did that one day with the 4 big theorems, and y'all did the rotating, and you're like, oh, there's the proof of that theorem, there's the proof of that theorem. One of the theorems said, for abelian groups, if the order of an abelian group is divisible by a prime, there has to be an element of that prime order, right? In fact, I think, didn't we do that for all divisors, not just primes? We at least did it for primes, right? Okay. So if P did divide the order of K, then K would have to have an element of order P. Okay, now here's why that can't happen. So let's call that element something, let's call it X, of order P. Okay, so then, we have X to the P to the identity. But also, what does it mean to be in K? Being in K means that that element raised to the nth power is also the identity. What?
P has to find in which one.
That's right, yeah, in fact, I probably shouldn't even written this part, I could have just gotten away with this part. You're saying that P would have to divide M because we're saying P is the order of X. And if the order of X is P, and X to the nth is 1, we have to have yeah, so actually Paul helped me think of a more elegant way of writing that. In fact, let me just erase a couple of things here. So we don't need this, and we don't need this, and we don't need a semicolon. We'll do. Sam?
Could you also use the fact that they H and K intersect trivially? And if you had an element X of order P, that would mean that X would be in K and X would be in H, but they intersect trivially.
Okay, one more time slower. Okay,
so if P did divide K, then K would have an element of X of order P. So X to the P would be the identity, which would mean that X was in H. Or, yeah, so X was in H, but they only intersect trivially.
Oh, that's clever. Yes, you could have done that actually. Okay, so just one more time. So Sam's approach would have been, if we did have some element of order P, then one thing that we would know about that element is it would be in this set, because if your P's power is the identity, certainly your P to the A's power is the identity. So X belongs to K, but also X belongs to H, and we know what belongs to both X and H, just the identity. So that would also work. Nice. Yeah, at this point there's a lot of ways to do the same thing, which is I think part of what makes the subject kind of tricky. I think you're finding that as well, probably. Okay, so that's K. So what that means then, so since P doesn't divide K, and for the order K, and the order K does have to divide P to the A times M. We must have the order of K dividing M, because it can't divide any of the P's. So that's half of it. Here's the other half. Okay. So now, I think Gaussian has a slightly more elegant, sleek way of doing this. I'm just going to write this way. Okay. Now, for any prime Q dividing M, prime q dividing m, q has to be not equal to p, because we already said p doesn't divide m. So q can't divide the order of h, and the reasoning is the same as what we did last time. Because now what we're saying is, well, if h did have, yeah, if the order of h was divisible by q, then h would have to have an element of order q, and we run into the same problem. All right, so q doesn't divide the order of h. So, no prime other than p divides the order of h. And thus the GCD of m and the order of h has to be 1, which means that since the order of h has to divide p to the a times m, the order of h actually has to divide just p to the a. Okay. Well, if the order of h divides p to the a and the order of k divides m, okay, let's just summarize this. We know that the order of h has to equal the order of h times the order of k. Which is p to the times m. Okay. So let me just try and get this out a little bit more clearly here, all right? We know that g is the direct product of h and k. So whatever the order of g is, which we know, that's p to the a times m, that has to be the product of these two orders. So the product of the order of h and order of k has to be p to the a times m. In the meantime, we're saying the order of h has to divide this piece here, and the order of k has to divide this piece here. Okay, what's the only way we're going to have two numbers, one dividing p to the a and one dividing m, that multiply to p to the a times m? It's got to be, like, the order of h has to be p to the a, the order of k has to be exactly m. We must have order of h equals p to the a, and the order of k equals m. Okay, so at this point, I just want to pause. I don't think we're going to get all the way through step 2. I can at least sketch that for you. But I'd rather tell you why step 1 helps with the classification. Did you have a question?
Oh, no, sir. I was
Okay.
shaking out.
All right.
I was excited.
So here's what step 1 does for us. All right, so suppose G is an abelian group of order, I'm going to go with something different this time. Let's say, I don't know, 84. Okay, this is just an example. So G is abelian order 84. All right, one thing that we know, 84 is equal to 7 to the first times 12. So I'm very purposefully writing this as p to the a for prime p times m. Okay, so that lemma, step 1, gives us an h, a subgroup h, of order 7 to the first, and k of order 12, such that G is isomorphic to h cross k. Okay, that's the conclusion of step 1. Step 1 says, well, if you look at this, and you take all the groups whose 7th power is the identity, that's a subgroup of order 7. And all the elements whose 12th power of the identity, that's a subgroup of order 12. And not only that, but G is the direct product of those two groups. Okay? And what's more in this case, because we have an H of order 7, well, what groups do you know of that have order 7? If you've got a group of order 7, what does it have to be isomorphic to? It's got to be Z mod 7. It's got to be cyclic, and a cyclic group has to be isomorphic to Z mod n if it's finite. So it's got to be Z mod 7 plus some other group which has order 12. And now you can rinse and repeat. With 12, you know the 12 is 2 to the second times 3. So you can use step 1 again. You can peel off some abelian group of order 2 squared. Now that's going to be trickier because I can't say an abelian group of order 2 squared is necessarily Z mod 4. It's one of the two options. That's where step 2 is going to come in. Step 2 tells me that even if I don't have an abelian system of prime order, I can still express it as a direct product of Z mod n's. Okay? So what step 1 does is it's part of the induction process. It's part of the process of peeling off factors and giving me those Z mod n's that are part of decomposition. Okay, let's see what we can get done from step 2. Step 2 is sneaky. I thought about it for a couple of days, and I did not get extremely far with it. Once I looked at the proof, I was like, oh, that's how they did it. And it was mostly ideas that I thought of, but it was in a combination I would not come up with even if you give me a few more days. Okay, so step 2, let's assume G is abelian of order a prime power. Abelian of order, and you'll notice I'm switching the exponent here, e to the n. And what's left? A be an element of maximum order. Okay, and we're going to show that G is really the cyclic subgroup generated by A, direct product with some subgroup H. I'm not specifying which one yet. Okay, so here's the idea. We are going to induct on this M. So the proof is going to be by induction. Okay, here's the base case. Assume M is equal to 1. Okay, wait. If M is equal to 1, what do we know? Yeah, G is abelian of just order of prime. Just a prime of the first power. That's cyclic. Right. Okay, so order of G is just p to the first. And so G is cyclic. Okay, so let A be in G of order P. All right, well then G is just the subgroup generated by A, and that's it. Okay, now I realize I promised that I would show that G was equal to the subgroup generated by A crossed with something. Okay, here's the something. Okay. That technically counts. Okay, so that's the base case. You gotta love it, by the way, when the base case is a theorem. Yeah. You remember when we were in foundations of math and the base case was checking that the sum of one term was equal to 1 times 2 over 2? Surely y'all did that in your foundations of math class. You're proving that the sum of the integers from 1 through n was n times n plus 1 over 2. In the base case, you're like, that's equal to 1. That's equal to 1. And now the base case is use this entire theorem that took us 2 days to prove. All right, I've got another one for you like that, if you're gonna do the CELO theorem problems. There's another theorem that has that kind of attitude. All right, so here's the other one. Here's the induction step. Okay, I'm gonna do this using something called strong induction. Here's what strong induction is. Okay, so what we typically call induction is weak induction. Weak induction means we assume that we've proven the prior case, the immediate prior case of the theorem. Here, we are going to assume we've proven all previous cases of the theorem, and now we're just focusing on p to the m. So we're gonna assume the theorem is true if our group order is any prime power, any power of p less than p to the m, okay? Let's see, how do I say this? Any prime power order of the group less than p to the m. And I'm not going to use that right away. It's going to come up later, maybe later, like during problem solving club, but it comes up later in the proof. All right. So let's let A, I've already done this. Well, let's just do it again. Let A have maximal order in G. Okay, I just realized the question to one of my earlier questions. You remember earlier I said we proved that if the order of G is divisible by prime, there has to be an element of that order, right? And I said, well, didn't we prove that for every divisor of G? Of course we didn't. If that were true, then there would have to be an element of G whose order is the order of G, and that would mean G is cyclic, and not all G groups are cyclic. I just realized that I engaged in that tomfoolery earlier, and I felt I should atone for it. So it's only true when the divisor is a prime. Okay, anyway, let A have maximal order in G. So we're assuming that A is the element of G that has the largest possible order in that group. Okay? So here's what I'm going to do to start building H. Let B be an element of G such that, first of all, B doesn't belong to the subgroup generated by A, so it's not a power of A at all. Sorry, not an element of. And B has minimal order, subject to this constraint. Now let me explain what I mean by that, okay? If I just said pick B to have minimal order, what would you pick? The identity, okay? So that's not what I mean. I mean pick B to have minimal order among things not in this subgroup, because the identity would automatically be in that subgroup. So we're saying pick the thing not in here that has minimal order, all right? I claim that the order of B is equal to P. And there's kind of a lengthy, complicated reason why it has to be. Here's what that is. Suppose by way of contradiction, that the order of B isn't P. Now, I'll just remind you at this point, what's the order of G? The order of G is P to the, what is it, P to the M? It's P to the M, okay? So when I'm thinking about B, the possible orders of B, what are those gonna be?
P squared,
Yeah, some power of P, it's gotta be some power of P. So if I'm saying that the order of B is not P, we already know it's not gonna be 1 because that would make it the identity. The identity's in the group generated by A. So the order of B has to be some other higher power of P, P squared, P cubed or something, right? Okay, so then, the order of B is equal to, and I'm trying to remember what I called this. So I think for the proof, I decided to let the order of A be P to the N. Again, the order of A has to be some power of P because it's in a group whose order is a power of P. And the order of B is going to be P to the L. For some L, I can say for this, an integer, L greater than 1. There we go. Okay, so now, okay, and this uses another theorem from early in the semester. We're throwing the entire kitchen sink with this theorem. Everything we prove in the semester is in this proof somewhere. Okay, now think, the order of B is P to the L. Does anyone know what the order of B to the P would be? We actually know what this would be. L. Not gonna be L. I can see why you would think that, but it's actually not L. Okay, let's see here. Let's say I tell you, so a different situation. X has order 12. Okay, what about x to the third? What would its order be? Ralph, what do you think?
4.
Be 4, because x to the third raised to the fourth power is the identity. Okay, x to the third to the fourth is x to the 12th. Here, if this is my order of B, and I raise that to the pth power, what's going to be the new order?
P to the L minus 1.
P to the L minus 1. Okay, so B to the P does not belong to this. Okay, wait, what is that? Yeah, you bet. Okay, so when I say B, the order of B is P to the L. Because this means that the order of B is P to the L, that means B to the P to the L power is the identity. Okay, so another thing that means, I'm actually happy to do this because this is not at all clear here. So what I've done here is I split P to the L into P times all the other P's. So if, for example, this had been B to the P to the fourth, okay, well that would also mean B to the P cubed would be, that's it for example there, okay? Okay. So there's a theorem that we have that says that if the order of this is some number, let's just call it m for a minute, then if A is a divisor of m, then B to the A has order m divided by A. And I know I'm like reusing every symbol in the book here because I've defined all of it already, but I was just searching for letters I could use. Okay. So that's why. Did that help, Paul? Cool. This is a tough one, isn't it? All right. So B to P does not belong to that single set. Did anyone figure out why that's true? Here's why. Oh, sorry, no, that's completely false. No wonder nobody can figure it out. It's the opposite of that is true. B to P has to belong to the cyclic set generated by A. Okay, here's why that's true. Okay. I said B was the thing of the smallest possible order not belonging to the cyclic subgroup. So if I identify something whose order is smaller than P to the L, then it has to belong to the subgroup. Yeah, I was also panicking because I didn't know if that was the next statement, then what would come after that. I think I now know what I can do with that. You know, if you're trying to prove something and you get stuck, consider the possibility that it's because you wrote something that is totally the opposite of true. That's actually the case more than a small amount of the time. All right, so b to the p belongs to this subgroup. Do you know what I'm gonna do with that? I'm gonna do like the first thing you think of when you say something belongs to brackets A. What is that? So b to the p is equal to A to something. We're running out of letters. I'm gonna use I. I think it's I. For some integer I. Okay. Now, if that wasn't enough, I further claim that I has to be a multiple of p. Okay? And because I have like 3 minutes left, and I want to show you like the major idea of what happens after this, I'm going to ask you to refer to the book. So I'm going to describe what happens here. Okay, so Gaussian proves this. He uses that. But there's an element of order P that is not in brackets A anyway. So what he does is he shows that if the minimal order thing that's not in the cyclic subgroup has order anything bigger than P, there's something in order P not in here anyway. Okay? Which means that the minimal order object not in this subgroup has to be order P. Here's why he does that. Here's what motivates the whole crazy train of reasoning here. So once we have an element B of order P not in this subgroup, here's what we do next. We take the map, the quotient map, B from G to G mod the subgroup generated by B. So we drop down to a quotient group, which he calls G bar. Okay? Now, if you take the quotient group of G, which has order, I think it was P to the M, modulo this subgroup, which we've now proven, or well, Gaussian's proven, has order P, then the order of this quotient group is P to the M minus 1.